How SCADA controls entire factories and power plants. Explained clearly. Imagine standing inside a modern power plant. Thousands of valves are opening and closing. Pumps are moving water at high pressure. Turbines are spinning at thousands of revolutions per minute. Generators are producing hundreds of megawatts of electricity. Temperatures, pressures, voltages, currents, flows, alarms, vibration levels, and safety interlocks are changing every second. Now imagine one operator sitting in a control room looking at large screens. With one click, he can start a pump. With one alarm, he can know that a boiler pressure is rising. With one trend graph, he can predict a problem before a machine fails. This is the power of SCADA. SCADA stands for Supervisory Control and Data Acquisition. It is a combination of hardware and software used to monitor, control, and collect data from industrial processes such as factories and power plants. It is used in water treatment plants, oil pipelines, chemical plants, substations, and manufacturing lines. SCADA is the nervous system of modern industry. Sensors are its eyes and ears. PLCs and RTUs are its reflexes. Communication networks are its nerves. Servers and databases are its memory. The control room screen is its brain interface, and the operator is the human decision maker. It helps engineers save energy, improve safety, and increase production. Today, we will understand SCADA clearly, from history to hardware to cybersecurity. Part 1. Before SCADA. When factories were controlled by hands and eyes. Before computers, factories were controlled manually. Operators walked around the plant with notebooks. They checked pressure gauges by eye. They opened valves by hand. They listened to machines to detect abnormal sounds. They touched bearing housings to feel overheating. They read analog meters every hour. In a small workshop, this was possible. But as factories became larger, manual control became slow and risky. A power plant may have thousands of signals. A refinery may have hundreds of pumps. A water network may spread across hundreds of kilometers. An electrical grid includes substations far away from each other. No human team could continuously observe every instrument manually. This created three major problems. First, slow response. If pressure increased suddenly in a remote pipeline, operators might know too late. Second, poor accuracy. Manual readings could be missed. Manual readings could be missed, delayed, or written incorrectly. Third, lack of centralized visibility. Management could not see the full plant. Management could not see the full plant condition from one location. Industry needed a system that could collect data automatically and allow remote control. Part 2. A short history of SCADA. The roots go back to early telemetry. Power companies needed to monitor substations and distant stations. By the 1960 seconds and 70 seconds, computers and communication systems made remote industrial supervision more practical. The term SCADA emerged around the mid-1970s. Early SCADA systems used large mainframe computers. Communication was slow. Many systems were proprietary, making inter-manufacturer communication difficult. But even those early systems changed industry forever. For the first time, operators could sit in one control room and monitor distant machines. In the 1980 seconds and 90 seconds, SCADA improved rapidly. Microprocessors became cheaper. PLCs became powerful. Graphical screens replaced simple text displays. From the 2000 seconds onward, SCADA entered the digital age. Ethernet, fiber optics, cloud connectivity, and advanced analytics became part of the SCADA ecosystem. Part 3. What SCADA actually does. Job 1. Data acquisition. This data comes from sensors. For example, a temperature transmitter sends boiler temperature. A flow meter sends water flow. A level transmitter sends tank level. A vibration sensor sends bearing condition. An energy meter sends frequency. These instruments convert physical quantities into electrical signals. Common industrial signals include 4 to 20 milliamperes, digital on/off, or communication through Modbus and Profinet. Job 2. Monitoring. SCADA displays live conditions on HMI screens. Operators see pump status, tank level percentage, and power output in megawatts. Instead of walking through the entire plant, an operator views the process from one room. This improves safety and speed. Job 3. Supervisory control. SCADA gives high-level commands like start pump 2 or change pressure set point. The actual fast logic is executed by field controllers. It supervises from a higher level. Job 4. Data logging. SCADA stores data in a historian. It helps answer, what was the pressure before the trip? How much electricity did we consume? This data is extremely valuable. Part 4. Components. Layer 1. Field instruments. These are physically connected to the process. If sensors are wrong, SCADA shows wrong info. Calibration is vital. Layer 2. Controllers. PLCs are for factories. RTUs are for remote sites like pipelines. IEDs are smart devices for power systems. They read signals and execute fast local logic. Layer 3. Communication. SCADA transfers data via fiber, radio, or industrial Ethernet. Protocols like Modbus and DNP3 are the languages machines use. If communication fails, the plant goes blind. Layer 4. SCADA servers, the brain that processes data. It handles thousands of tags, data points with values, units, and alarm limits. Layer 5. HMI stations. Layer 5. HMI stations. What operators see. Good HMI design helps quick decision-making. Layer 6. Historian. It records every second for analysis, quality control, and AI-based maintenance. Part 5. How SCADA controls a factory. Let's take a bottling plant with tanks, fillers, and packing machines. Step 1. Sensors collect data on levels and flow. Step 2. PLCs run local logic. If a tank is low, it starts a pump. If a bottle is missing, the filler stays closed. This fast logic protects the machine and production. Step 3. SCADA displays the whole plant. The operator sees line speed, tank levels, and energy use from one room. They can increase speed directly from the screen. Step 4. SCADA sends commands. If an alarm for low air pressure appears, the operator identifies the cause and starts a standby compressor within seconds, preventing downtime. Step 5. SCADA records data. Day-end reports reveal root causes for downtime, like recurring leaks, converting raw data into industrial intelligence. Part 6. Power plants. Power plants are critical SCADA applications. Even a small mistake can cause grid disturbances. SCADA helps operators supervise the entire complex safely. Boiler monitoring is first. SCADA monitors steam pressure, temperature, and drum level. Drum level is critical. Too low and tubes overheat. Too high and water can damage the turbine. Turbine monitoring is next. The turbine is expensive. SCADA monitors speed, vibration, and oil pressure. At 3,000 revolutions per minute, even a small vibration increase is serious. SCADA trends help see problems before failure. The generator converts mechanical energy into electricity. SCADA monitors megawatt output and frequency. For grid connection, these must be balanced to maintain exactly 50 or 60 Hz. Power goes to the switchyard, where SCADA controls breakers and transformers. In grid systems, generation and demand must be balanced continuously. SCADA helps keep the lights on. Part 7. SCADA versus PLC versus DCS. PLC is the controller. SCADA is the supervisory system. DCS is for continuous processes like refineries. Modern industry is blurring these boundaries. Part 8. Alarms. Too many alarms confuse operators. This is an alarm flood. Good SCADA design uses priority levels and clear messages to help engineers respond quickly. Part 9. Trends. Graphical views of values over time. If a pump current slowly increases over weeks, trends reveal the friction or blockage before the pump actually breaks down. Part 10. SCADA and power grid control. Grid operators monitor generation, transmission loading, and frequency. Advanced systems like energy management help balance the whole grid. Part 11. Communication. How machines talk. SCADA asks the PLC, "What is the pressure?" PLC replies, 6.8 bars. Thousands of values are exchanged many times per second. Protocols are the language. Part 12. Redundancy. Critical plants cannot go blind. Important systems use dual servers and networks. If the active server fails, the standby takes over instantly. This is like a spare engine. Part 13. Cybersecurity. Modern SCADA connects to business networks, creating risks. A cyber attack could stop pumps or change set points. OT security protects the physical process. Security focuses on network segmentation, firewalls, and access control. It's not just about data, it's about human safety and production continuity. Part 14. Safety interlocks. Part 14. Safety interlocks. Safety should not depend only on SCADA. Mechanical valves and hardwired stops ensure fast action. SCADA supervises, but safety systems protect. Part 15. Real benefits. SCADA gives faster fault detection, energy efficiency, and preventive maintenance. It converts plant operation into useful data for management. Part 16. Pumping station. Imagine a pumping station. If a pump trips due to overload, the SCADA historian reveals if current was gradually increasing, helping maintenance find the bearing issue quickly. Part 17. Boiler trip analysis. After a trip, engineers use the SCADA historian to see the sequence. Feed water flow reduced first, then level, then trip. The power of timestamped data reveals the root cause. Part 18. Modern evolution. SCADA now connects to MES, ERP, and AI models. Data can predict failures months in advance, linking production directly to business planning. Part 19. Design. Part 19. Design mistakes. Avoid too many colors or animations. Good design is simple and clear, helping operators answer, what is running, what is abnormal, what action is needed. Part 20. Future of SCADA. Smarter, faster, and more connected. We will see more AI anomaly detection, cloud historians, and augmented reality. SCADA will continue to give engineers vision. When we switch on a light or drink clean water, we rarely think of the system behind it. Behind the modern world is a silent digital guardian. That system is SCADA. SCADA does not replace operators, it gives them control. Without it, modern industry would be slower and riskier. SCADA is the invisible layer that keeps the modern world running.